Today we're going to explore one of the most elegant experiments in physics history, the Millikan oil drop experiment. But we're not just going to talk about the physics. We're going to learn how to analyze real, messy data and discover fundamental truths hidden in apparent noise. In 1909, Robert Millikan faced a profound question. Is electric charge continuous, like water from a faucet, or is it quantized, coming in discrete packets? This wasn't just academic curiosity. The entire atomic theory depended on the answer. Think about it this way. If I hand you a glass of water, you can pour out any amount you want, half a cup, 1.3 cups, pi cups if you're feeling mathematical. That's continuous. But what if charge doesn't work that way? What if charge is more like money? You can have $1, $2, 50 cents, but you can't have 0.73 to $1 in actual physical coins. There's a smallest unit, the penny. Could charge have a fundamental unit too? Millikan's brilliance was in his experimental design. Let me walk you through it step by step, because understanding the setup is crucial to understanding why the data looks the way it does. Here's the setup. Two metal plates create a uniform electric field. Tiny oil droplets, about 1 micrometer in diameter, are sprayed between the plates. These droplets pick up electric charge, usually by friction during the spraying process. Each droplet experiences two forces. First, gravity pulls it downward. Second, if the droplet is negatively charged and we make the bottom plate negative, the electric field pushes it upward. By adjusting the voltage, Millikan could balance these forces. When the forces balance perfectly, the droplet hovers in mid-air. From the voltage needed to achieve this balance, combined with the droplet's mass and the strength of gravity, we can calculate the charge on that droplet. Sounds simple, right? But here's where it gets interesting and where real science begins. When you actually do this experiment, you don't get clean, obvious results. You get noise. You get measurements that seem all over the place. Let me show you what real data looks like. Here are 8 measurements. Look at them. 3.2, 4.8, 6.4. They're not identical. They're not even close to being simple multiples of each other. If you were a student seeing this data, you might think the experiment failed. So here's a question for you. Does this messy data prove that charge is continuous? After all, we're seeing different values. Doesn't that suggest charge can take any value? Think about it for a moment. The answer is no. And this is the crucial lesson. Just because data looks messy doesn't mean there's no underlying pattern. We need the right tools to find the signal in the noise. This is what data analysis is all about. The first step in analyzing any real-world data is cleaning. Not all measurements are equally reliable. Some droplets evaporate slightly during measurement. Some pick up additional charge from stray ions. We need to identify and handle these outliers. Look at our data again. Most values cluster between 1.6 and 9.6. But imagine if one measurement was 50. That would be suspicious. Either that droplet is special, or something went wrong with that measurement. A common rule is the 3 sigma rule. Calculate the mean and standard deviation of your data. Any point more than 3 standard deviations away from the mean is a candidate for removal. But be careful. Don't remove data just because it doesn't fit your hypothesis. Let's say measurement 5, 8.1, was taken when the droplet was evaporating. We might remove it. But we must document why we removed it. Scientific integrity demands transparency in data cleaning. Once we've cleaned our data, the next step is visualization. The human eye is incredibly good at spotting patterns. A histogram is the perfect tool for this. Let me show you how to construct one and what to look for. A histogram divides your measurement range into bins or buckets. Then you count how many measurements fall into each bin. The height of each bar tells you the frequency. This transforms a list of numbers into a visual pattern. Here's what our histogram might look like. Notice something interesting. The bars aren't evenly distributed. There are peaks at certain values, around 1.6, around 3.2, around 4.8. This is not random noise. This is a pattern. Here's another question. What do these peaks in the histogram tell us? Why would certain charge values appear more frequently than others if charge were truly continuous? Take a moment to think about this. The peaks suggest that certain charge values are preferred. This is exactly what we'd expect if charge comes in discrete packets. If every measurement is a multiple of some fundamental charge, then we'd see peaks at 1e, 2e, 3e, and so on. Now comes the detective work. We need to find what that fundamental unit is. We have peaks in our histogram, but what's the spacing between them? This is where mathematical analysis meets physical intuition. First, identify the center of each peak as accurately as possible. Then calculate the differences. If our peaks are at 1.6, 3.2, 4.8, 6.4, then the differences are all 1.6. That's our candidate for the elementary charge. Peak 1 is at 1.6 times 10 to the negative 19 coulombs. Peak 2 is at 3.2 times 10 to the negative 19 coulombs. That's exactly twice peak 1. Peak 3 is at 4.8 times 10 to the negative 19 coulombs. That's exactly 3 times peak 1. This strongly suggests that the elementary charge, which we call E, is 1.6 times 10 to the negative 19 coulombs. Every measurement is a multiple of this value. But there's an even more powerful technique. Instead of just looking at peaks, we can use a mathematical approach called the greatest common divisor method. This works even when our data is noisier. Here's the idea. Take all your charge measurements. Find the largest number that divides evenly into all of them within experimental uncertainty. That number is your candidate for the elementary charge. Look at how this works. When we divide each measurement by 1.6, we get integers. 1, 2, 3, 4, 6. Perfect whole numbers. This is the smoking gun. This is quantization. So how do we rigorously test whether a quantity is quantized or continuous? This is a general skill that applies far beyond the oil drop experiment. Let me give you a systematic approach. First criterion. Take pairs of measurements and compute their ratios. If charge is quantized, these ratios should be close to small integers. 3 to 1, 2 to 1, 5 to 3. If charge is continuous, you'd expect to see ratios like 1.7, 3 to 1, or 2.89 to 1. Second criterion. Take your candidate elementary charge and divide every measurement by it. Plot the results. If you get a histogram with peaks at integers 1, 2, 3, 4, you found quantization. If you get a smooth distribution, it's continuous. This is what that plot looks like for our data. Clear peaks at integer values of n. This is unambiguous evidence of quantization. No continuous quantity would ever produce this pattern. Third criterion. For the mathematically inclined, use a chi-squared test to compare your data against two models. Model 1. Charge is quantized with elementary charge E. Model 2. Charge is continuous. The model with lower chi-squared value fits better. Now let me be honest with you. Real experiments are messier than textbooks suggest. Millikan himself faced challenges that took years to overcome. Understanding these complications makes you a better scientist. First challenge. Oil droplets evaporate. As they lose mass, the force balance changes, and your calculated charge drifts. Millikan spent considerable effort finding oils with very low vapor pressure to minimize this effect. Second challenge. The formula for air resistance on tiny droplets, called Stokes' law, breaks down at the micrometer scale. Millikan had to develop corrections for this. Getting the physics right matters for getting the right answer. Third challenge, and this is important from a scientific integrity standpoint. Millikan has been criticized for cherry-picking data. He apparently discarded measurements that didn't fit his hypothesis. This is a cautionary tale. Always report your data selection criteria transparently. Let me drive home why this statistical approach is so powerful. It's not just about the oil drop experiment. This is a general methodology for discovering fundamental constants in noisy data. And it's used everywhere in modern physics. Imagine you're a 19th century chemist. You measure the mass ratios when elements combine. Hydrogen and oxygen make water in a ratio of 1 to 8 by mass. Carbon and oxygen make carbon dioxide in certain ratios. From hundreds of messy measurements, you can deduce that atoms have specific masses, not continuous masses. Or imagine you're measuring the rotation speeds of stars in galaxies. Individual measurements are noisy, but when you plot enough data, a clear pattern emerges. The rotation curves are flat, not declining. This led to the discovery of dark matter. Pattern recognition in noise is fundamental to science. Millikan's original value was 1.592 times 10 to the negative 19 coulombs, pretty close to the modern value. But let me show you how much progress we've made. The modern accepted value is 1.602176634 times 10 to the negative 19 coulombs. Notice something interesting? This value is now defined exactly. It's no longer measured. In 2019, the SI system was redefined. The elementary charge E is now a defined constant, and the coulomb is derived from it. This is how science progresses. What was once measured becomes so well established that it becomes the definition. Let me give you a practical workflow you can use for any experiment where you're trying to determine if a quantity is quantized. This is your step-by-step guide. Step 1. Collect enough data. For a robust statistical analysis, you need at least 50 measurements, preferably more. 1 or 2 measurements tell you almost nothing. Statistics requires volume. Step 2. Clean your data systematically. Apply the 3 sigma rule. Document every data point you remove and explain why. Never hide data that doesn't fit. Step 3. Make a histogram. Choose your bin width carefully. Too narrow and you see only noise. Too wide and you smear out the peaks. A good rule of thumb is the square root of your number of data points for the number of bins. Step 4. Identify peaks. Use peak finding algorithms if you have many peaks. Calculate the spacing between peaks. This gives you your candidate fundamental unit. Step 5. Test your hypothesis. Divide every measurement by your candidate fundamental unit. Do you get integers? Plot the results. The proof is in the distribution. Step 6. Quantify uncertainty. What's the spread in your measurements divided by the candidate value? This tells you the precision of your determination. In scientific papers, you must always report uncertainty. Before we wrap up, let me warn you about common mistakes students make when analyzing this type of data. Learn from others' errors. Pitfall 1. Don't assume the smallest charge you measure is the elementary charge. What if all your droplets happen to carry at least 2 electrons? The smallest measurement might be 2e, not e. You need to look at the pattern of differences, not just the minimum value. Pitfall 2. Every measurement has uncertainty. If your candidate elementary charge is 1.6 and you measure 1.58, that might still be consistent with 1e if your uncertainty is plus or minus 0.05. Use error bars. Pitfall 3. Don't overinterpret small datasets. With only 5 data points, you can convince yourself of almost any pattern. Statistical significance requires adequate sample size. Be humble about what small datasets can tell you. The Millikan oil drop method isn't just historical. Variations of this technique are still used today in cutting-edge research. Let me give you some examples. Modern physicists use optical tweezers, which trap particles using focused laser beams instead of electric fields. This allows study of individual molecules and even direct measurement of forces between DNA base pairs. The analysis techniques are the same. Measure many times. Look for quantization. In quantum dot research, scientists measure the discrete energy levels of electrons confined in tiny semiconductor crystals. The data analysis is pure Millikan style. Make histograms of energy measurements. Look for equally spaced peaks. Find the fundamental energy quantum. Single molecule force spectroscopy measures the forces needed to unfold proteins. Each protein domain unfolds at a characteristic force. You measure hundreds of unfolding events, make histograms, and identify the discrete unfolding pathways. It's Millikan in biology. Finally, let's step back and appreciate the deeper significance. The Millikan experiment didn't just measure a number, it revealed something profound about the nature of reality. It showed that nature is fundamentally discrete, not continuous. Charge comes in packets. Later we learned that energy is quantized, angular momentum is quantized, even space and time might be quantized at the Planck scale. The universe has a graininess to it. It demonstrated that hidden order exists in apparent randomness. Those messy measurements that seem to have no pattern actually encoded one of nature's fundamental constants. This is what drives physicists, the faith that beneath the chaos there are simple, beautiful laws. And it proved that with the right analytical tools, humans can discover these truths. We don't need perfect instruments or noise-free data. We need good statistics, careful reasoning, and persistence. That's the real lesson of Millikan. Let me summarize what we've learned today. You now have a complete toolkit for analyzing quantized versus continuous data. The Millikan oil drop experiment elegantly demonstrated that electric charge is quantized, coming in integer multiples of the elementary charge, E equals 1.6 times 10 to the negative 19 coulombs. That analysis begins with cleaning. Remove outliers systematically using statistical rules like 3 sigma, but always document what you removed and why. Scientific integrity demands transparency. Histograms are powerful tools for pattern recognition. They transform lists of numbers into visual structures where peaks and gaps become obvious. Choose bin widths carefully to balance detail and clarity. Testing for quantization requires multiple approaches. Check if ratios are integers. Divide by candidate values and look for peaks at integers. Use statistical tests like chi-squared. Converging evidence from multiple methods gives confidence. The skills you've learned today go far beyond oil drops. Whenever you have noisy measurements and suspect an underlying discrete structure, use these techniques. Histograms, peak finding, greatest common divisor analysis. They work everywhere. Finally, appreciate how far we've come. Millikan worked with primitive equipment and got within 1% of the true value. Modern techniques achieve parts per billion precision. But the fundamental approach, the statistical analysis of many measurements, hasn't changed. Now it's your turn. Find a dataset. Any dataset where you suspect quantization. Maybe it's spectral lines. Maybe it's step heights in atomic force microscopy. Maybe it's digital signal levels. Apply what you've learned. Make histograms. Look for peaks. Find the fundamental unit. Discover the hidden order in the noise. That's what scientists do. Good luck and happy analyzing.